let's see what conjugation does to some group elements. We start with S3, permutation group, take the element 1, 2, and we conjugate it with 1, 3. So we need a 1, 3 inverse at the back. But of course, since 1, 3 is its own inverse, that's the same as 1, 3, 1, 2, 1, 3. And now we multiply some cycles. So we start with 1, 1 goes to 3, nothing happens to 3 here, 3 goes back to 1, which means we can just omit this 1, that would be a 1 cycle. Now let's continue with 2, 2 goes to 1, and 1 goes on to 3. So we write a 3 here, and let's check that this closes. 3 goes to 1, 1 goes to 2, 2 stays, so that's fine. So by conjugation we got the element 2, 3. Here's a different example. Let's conjugate the same group element again, the 1, 2, but this time with a cyclic permutation with 1, 3, 2. So what's the inverse of 1, 3, 2? That's the other cyclic permutation. That's 1, 2, 3. And now let's calculate this product. So 1 goes to 2, 2 goes to 1, and 1 goes on to 3. So that's 1, 3. Now what happens to 3? 3 goes to 1, 1 goes to 2, 2 goes to 1. So we can close this parenthesis here. And just for consistency, let's check that 2 is mapped back to 2. So 2 goes to 3, 3 stays, 3 goes back to 2. That worked. So we always got, again, a 2 cycle after conjugation. And actually, we will see that this is true in general. The cycle structure will be conserved for permutations under conjugation. Let's look at some other group. Let's look at SO3, something completely different. Rotations in 3 space, or you could say orthogonal 3 by 3 matrices with determinant 1. So group element could be this one here, R index n of phi. What do I mean by this? This is a rotation matrix which rotates about the axis n by angle phi. Now we conjugate this with some other element of SO3. So we multiply with S and S inverse on the left and on the right. And I claim that what we get is a rotation about the axis S times n by the same angle phi as we had on the left. Well, why is that? Let's do some linear algebra. When we calculate the eigenvalues of this matrix here, there will be an eigenvalue 1, because we leave this axis of rotation invariant. We rotate about this axis, so the axis n is an eigenvector with eigenvalue 1. And then if this phi is a typical phi, maybe a rotation about pi half or something, there will be no more eigenvectors. Everything is turned away. No more real eigenvectors, but too complex. No more real eigenvalues, but two complex eigenvalues, e to the plus minus I phi. Now, the eigenvalues don't change when we conjugate. The characteristic polynomial wouldn't change under this operation. So we have the same eigenvalues over here, which means that this is also a rotation matrix about some axis, the axis we don't know yet, but the same angle, because the angle is just the angle here from the eigenvalues. Okay. What about the axis? I claim that this axis here is just Sn. Well, let's try. What happens if we take S Rn of phi S inverse and multiply with S times n. So the S and S inverse cancel. That is, we have S R index n of phi times n. But now we said that this is a rotation about the axis n, so it leaves this n here invariant. So that's just S times n. And now we see that this rotation leaves this axis here invariant.